Welcome to Lab 2. This is motion of a falling object, where we record a falling object and analyze it through tracker and make computational models to compare its movement. So getting into the physics for falling objects means that this object is under constant gravitational force in the downward direction towards Earth. And in this lab, we use the velocity update formula V final equals V initial plus F net by the mass times delta T, and position update formula, which is R final equals R initial plus V delta T. So in a falling object, we should also account for drag force, which is air resistance, which acts opposite to the object's motion. And if for this lab, it's proportional to the square of the speed, and we use a formula of F drag equals B times V squared, where B is a proportionality constant and V is the speed. So getting into the experiment, this is how I set up tracker. It's very similar to lab 1. I used a free falling object I recorded myself, and I put it into tracker, and I tracked the several points. So once that has been tracked, this is a screenshot of what I had accomplished through the video analysis program, and you can see that the y direction position time graph had a parabolic curve as expected, and the x direction is of no interest because it is only moving in the y direction as it is a free falling object. Now let's get into the computational model. First, we're going to model with no drag, so the total force acting on the object is only the gravitational force, and we are not accounting for the drag force. This is a snippet of my code. You can see that we're starting with time t. We're starting with the position that my observation had started with, and we're starting from rest, which is why the velocity is 0. And here b is 0 for the drag proportionality constant, and W is the gravitational force. So F net is the gravitational force plus 0. And here what we're doing is we're updating the velocity and position using the update formulas described earlier in this presentation. So now we see the chart that I got from getting these values and putting them into my spreadsheet. So this is just observed data and model without drag. You can see that there is a little bit of difference, and the observed model actually goes farther than the model without drag. And now we get into the computational model, including drag force. So as a refresher, drag force is proportional to the square of the speed, and I adjusted the proportionality constant to mimic the observed values. So this is the proportionality constant that I use, so I get close to the observed values when accounting for drag force in my model. So this is on another snippet where you can see how the drag force is being added right here, and it's just to show that the drag force is now being added to the net force. And now this is a graph of all three together, and you can see how the model with drag is now closer to the observed data than the model without drag. And finally, when it comes to terminal velocity, for the model with drag and without drag, both the velocity time graphs look very similar to each other in the time frame that was being used. Neither of them reached terminal velocity in this model described in my glow script, and they are decreasing at a constant rate. However, I must add that gravity-only models can never reach terminal velocity, while real-life experiments with drag force will always reach terminal velocity. To answer the second question, between an object that starts from rest and starts with an initial velocity, their terminal velocity does not change. However, if an object is started with a velocity greater than the terminal velocity, it will slow down to that terminal velocity.